Hello, today we're going to discuss solar PV and thermal systems and how fire service operations go with those. A little bit about the company. Delmarva Emergency Training Concepts was created in January of 2016, looking for a new approach to training and tactics. We've developed courses to better the students wishing to further their knowledge. As far as I go as the instructor, I have over 10 years in the fire service. I've served as a volunteer fire captain and an emergency medical technician basic in the state of Maryland. I've worked in several fields involving technical rescue and hazmat in the oil and gas industry, and I saw training and wanted to make a change for the better. When we talk about solar cells, these are thin wafers of silicone similar to computer chips, however much bigger and much cheaper. These solar cells are made of silicon, which is very abundant, simply compressed sand. It's non-toxic and safe, and it allows the light to carry energy into the cell. These cells convert sunlight into energy, electric current, however they do not store the energy. Essentially, sunlight is the fuel, as you would use fuel in a generator. When we talk about modules, this is a group of cells that make up a module, and a group of modules make up an array, as you see in the picture below. They generate electricity from sunlight and have no moving parts. They're generally rated between 125 and 435 watts each and produce anywhere from 24 to 48 volts of DC power. When attached in a series, the voltage increases. The National Electric Code, or NEC, permits for 1 and 2 family dwellings PV system voltage up to 600 volts DC. For multi-family dwellings and other large buildings, the PV system voltage can be even greater. Most residentials have anywhere from 15 to 40 panels. Residential systems will generate anywhere from 2,000 to 12,000 watts or 2 to 12 kilowatts in optimal sunlight conditions and between 120 and 600 volts DC. There are different types of PV modules. You see here the most common is the laminated tempered glass with an aluminum frame. We also see flexible laminated modules that are very common on the West Coast and growing on the East Coast. Building integrated PV, which takes the place of light concrete tiles as seen here. Solar shingles, which actually takes the place of your roof covering in converting electricity. There are two common types of solar energy systems: thermal systems and photovoltaic or PV systems. Thermal systems heat water for domestic heating and recreational use, such as hot water, heating for pools, and radiant heating and air collectors. They typically have smaller solar panels than a PV system. Here's an example of a thermal system utilizing an active closed-loop solar water heater. You have your flat panel collector. You have your antifreeze style glycol fluid through the collector loop. You have a pump that will pump the glycol solution from the roof to the water heater or vice versa. You have a double wall exchange heater. You have your solar storage or your backup water heater attached, flowing the hot glycol solution into your cold water supply. And then that hot water will return back to the house for use. With photovoltaic systems, or PV, they convert sun rays into electricity. Some PV systems have batteries to store electricity. Other systems feed unused electric back into the grid. Photovoltaic systems have three primary components: modules, inverters, and the conduit. Panels are roughly 30 by 50 inches in area and weigh anywhere from 30 to 35 pounds each. Here's an example of a photovoltaic system. You have your solar array, which carries DC power through the conduit into the inverter, which then converts it to AC power to be utilized in the facility. You can also have battery storage and generators attached to the inverter for power outages or off-grid systems. There are two types of PV systems, grid-connected and off-grid, otherwise known as remote storage. This is an example of a grid-connected system. Utilizing power from the power grid coming into the utility meter, we are then going to come off of that with your inverter and your PV modules that will provide electric to the house. Again, these can backfeed to the power grid. An off-grid photovoltaic system, as you see here, will have all the components we listed. They will just not have any connection to the grid system, but they will always have some sort of battery storage or battery bank to store power when not needed to be used later. Off-grid systems can also have wind power, water power, and backup generators, as mentioned before, to provide energy at night when they're unable to make. When extinguishing battery fires, you want to utilize CO2, foam, or dry chemical extinguishers. Do not cut into the batteries at any time. Keep in mind that if corrosive fumes come in contact with certain metals, they will produce toxic chemicals and explosive gases. Always wear your PPE and SCBA. You want to be careful with metal tools around these batteries as well. Our primary concerns are that the mounting systems, are they structurally sound? That the roof is properly weatherproofed? That the electrical equipment is correctly installed according to applicable codes? That there are two main types of loads to consider, dead loads and wind loads. Dead loads is the load always placed upon the roof. Wind loads are additional loads placed with high winds that will pull on the panels and push. The roof structure must be capable of supporting these dead loads. Most modern truss roofs are capable of handling the extra dead load provided that the roof is not masonry. Masonry roofs often require a structural analyst or removing the existing product and replacing it with composite in the area of the PV array. Attachment methods must be capable of keeping the PV array on the roof or the relevant structure in case of high winds. Different examples of mounting systems, as you can see here, solar panels are either installed by stand mountings or ground mounts, flush mounting on the roof, or building integrated arrays, as you see here on the right side. When we talk about stand mounts, this is the universal mounting system used for ground and rooftop installations. It's a grid-like system of support of aluminum or steel that are fixed directly to roof joists. Or they may use non-penetrating concrete blocks as bases to hold the stand mounts into place. Flush mounting, these panels are raised several inches above the roof deck to allow for air circulation. Brackets are attached directly to the roof, and they may be hard to see at night due to design. We talk about building integrated arrays. These serve as a structural element. It does reduce added weight, and photovoltaic shingles could be subject to high wind. It's very difficult to see these during the nighttime from the ground, and this is where pre-planning is very important. Here are some examples of building integrated systems. As you see on the left, they've utilized solar panels in place of windows to provide electricity in the building while giving it that same appearance. The photo to the right, they've installed solar panels into an overhang to keep the weather from coming into the doors while providing electricity. Here are some examples of roof racking. As you see, they are attached directly to the roof. Most commonly, they are constructed of aluminum. When we talk about racking connectors, this is what actually attaches the solar panel to the roof racking. Most commonly, these are nothing more than a friction connector holding it down in place. With inverters and disconnects, modules are always wired to an inverter, which converts the DC voltage to AC voltage, and then feeds the electricity back to the main power distribution panel. The inverter requires AC from the power company. Shutting off the main electrical breakers also shuts down the inverter. On new construction, inverters will most likely be installed within the building. Inverters can be mounted inside or outside of the building. With on-grid systems, inverters are typically located near the main electrical panels. Off-grid system inverters are either inside or outside the building, but they may also be found in separate buildings that contain a generator or battery storage. Also, the inverter may be near devices or appliances the panels provide power to. Disconnects are often mounted on the inverter to shut off DC entering and AC leaving it. These disconnects are primarily used by techs to service the inverter. DC disconnects do not shut off power in the DC conduit. It just keeps the power from entering the inverter. DC conduit is still live between the array and the inverter or the DC disconnect. There is no rooftop disconnect to kill the DC power in a conduit. PV arrays use an inverter to convert the DC power produced by the AC modules. For safety reasons, a circuit breaker is provided both on the AC and DC side to enable maintenance. When we talk about connectors, there are two main styles of connectors. As you see here, this MC1 connector is what we refer to as a friction connector. It's just simply a push-pull to connect or disconnect. An MC4 is a different style connector that, while still is a push-pull, it has small tabs that have to be pushed in to release the connector. You can see here you insert the male connector into the female connector. This allows you to daisy chain these panels, creating more voltage. To disconnect an MC4 connector, you need to utilize a disconnect tool. You can also utilize a pair of needle nose pliers when a disconnect tool is not available. With microinverters, these are connected to each module. These simply turn this module into what we refer to as a smart module, allowing it to power on and power off as needed depending on sunlight. Labels on the main service panel will indicate the PV system presence. Labeling may also be outside or inside the main panel. You want to look for these dedicated breakers for the inverter. It may be labeled solar disconnect or some variation thereof. These breakers may be in sub-panels, but there will always be a label on the main electrical panel stating the presence of a second generating source on site. Labels may be the only identifier you might see, as the array may not be visible and the inverter may be in the fire. You always want to look for these labels. Here are some examples of different labels you may see in and outside of the facility. We're talking about fire department operations at solar arrays. With thermal systems, these can obviously impact fire department operations and may also be part of the fire problem. While you can cut the PEX tubing that supplies the glycol solution, you run the risk of thermal burns from the hot glycol as well as creating slippery conditions. PEX lines are rated at 150 degrees Fahrenheit. The best practice is to pinch off the line with a squeeze-off tool as seen below. With PV systems, these also can impact your fire department operations and may also become part of the fire problem. When you can disconnect power, there is still a possibility of energy from the panels, similar to gas remaining in a gas line. Severely damaged PV arrays are capable of hazardous conditions up to electrocution and can create unexpected electrical paths, such as metal roofs, gutters, and array components. The black cable connecting each panel carries voltage and increases as it goes from panel to panel. Do not cut this cable at any time. Do not cut into or walk across the PV modules or arrays. Breaking the protective glass could release all inherent energy in the entire PV system. You always want to utilize PPE and SCBA while operating around PV systems. Firefighting gloves and boots offer limited protection and are not equal to electrical PPE. You always want to look at a size up when considering your PPE for the situation. Locate if the panels are present, get your system information, and what type of system, whether it be thermal or photovoltaic, and locate any electrical disconnects. Here we see a study from the UL where they looked at boots that firefighters commonly wear. They looked at 3 different styles, as you see accordingly on the left. From the chart there, you can see that styles 1 and 2, which are leather constructed, new, offered the best protection and were a safe option, while the leather style offered an electrocution hazard of milliamps in DC. The same goes for gloves, as UL studied these, looking at different characteristics. As you see to the left, gloves 1, 2, and 3 were sampled. They were looked at new, soiled, wet on the outside, and wet on the inside. As you can see, the best protection were new gloves that were dry and not dirty. They offered the best protection, while wet or dirty gloves offered the least protection and still could result in electrocution. When looking at the size up, you might be able to see this array from the street as you arrive. However, looking at this structure, you might not see this one as you first arrive, but while conducting your 360. However, you may not see this solar array on the lower roof section, especially at nighttime. Do you think you'll see this one at night while conducting your 360? Maybe conduit coming from the roof could be your only clue, so you want to make sure you're looking for it. You want to inform the IC that a system is present, and they must relay that information to responding units. You want to use a stay clear approach. You want to shut down as much as possible utilizing lockout tagout. You want to disconnect at the inverter, battery controller, and the battery bank as an extra measure of safety. Remember, PV panels are 120 volts to 600 volts DC. If operation requires attempting to block light to the PV panel to protect firefighters, a tarp may be used. Effectiveness of the tarps to interrupt power generation varies with the type and the tarp material. UL conducted a study showing that heavily dense woven fabrics and dark black 4mm plastic reduced the power to near zero. Here's some of that research they conducted. They started with a green canvas salvage cover, commonly referred to as military salvage covers. And as you see here, the test results were 3.2 open circuit volts and 0 short circuit amps. This tarp was safe to use. However, if this tarp was worn, as they most commonly are, and has rips or tears or holes in it, it is not a safe option. Next, they evaluated the heavy-duty red vinyl salvage covers we commonly see on fire apparatus. These test results were 124 open circuit volts and 1.8 short circuit amps. This was an electrocution hazard. They should not be utilized. They also looked at blue plastic 5.1 mil all-purpose tarps. These are commonly used by homeowners and found at many home improvement stores. These test results were 126 open circuit volts and 2.1 short circuit amps. Again, this was an electrocution hazard. The final product that they looked at was disposable 4mm black plastic film. The test results were 33 open circuit volts and 0 short circuit amps. This was again deemed safe. The nice part about the 4mm black plastic is if you were to tarp a panel, you do not have to return to retrieve it, as it is very cost effective. If light can be seen through the tarp, it should not be used. A wet tarp may become energized if it contacts a damaged PV equipment and can conduct dangerous current. The tarp must be secured down on all sides to not lose its covering ability. And you always want to look at risk versus reward. Is it worth the risk to cover arrays, especially damaged arrays, to accomplish venting or overhauling? When looking at wood and foam to utilize for a PV system, water conductivity, voltage, and distance and spray patterns often affect electrical shock hazard. UL research has shown that the use of a fog pattern with a minimum of 10-degree cone angle with a distance of 5 feet from a 1,000-volt DC source detected no current leakage back to the operator. A smoothbore nozzle required a 20-foot distance with that same 1,000-foot DC current, obviously using these in a small arc pattern. Because of its high conductivity, salt water should never be used on live electrical equipment. Firefighting foam should also not be relied on to block light on these solar panels, as they are proved to be ineffective and will simply wash off with time. Outdoor solar electric boxes are not water resistant to fire streams. They will collect water and present an electrical shock. No matter what the system, remember, applying water directly to any energized electrical equipment endangers a firefighter to shock. Turn off the main breaker at the electrical panel. Fire department floodlights on trucks are bright enough to generate electricity, according to UL research. Light from a fire as far away as 75 feet was able to produce a current. Light from a full moon will not energize your PV cells, as it is simply a reflection. However, lightning is bright enough to create a temporary surge of electricity. At night, apparatus roof racks does not produce enough light to generate the electrical hazard. If your department carries non-contact voltage detectors, they only detect AC voltage, not DC voltage unless specified. When talking about roof operations, remember solar panels can impact our firefighting operations, especially these PV systems. Proximity to any fire involving a photovoltaic system will also bring with it an increased risk of inhalation of toxic vapors, so make sure you're utilizing your SCBA. Should an array become involved in a roof fire, use a fog pattern at a minimum of 10-degree fog. When looking at safety, shock is the primary danger to firefighters. Momentary contact with low DC voltage may produce continuous shock, thermal imagery, or ventricular fibrillation. You also have to be cognizant of tripping or falling over the raceway or other items on the roof line. Possible earlier roof collapse due to extra weight, especially under a heavy fire load, needs to be considered when dealing with PV systems. Arrays can accommodate snow and debris and other added weight. Hot water scalds with the thermal systems. Electrical shock due to intentionally or inadvertently cutting into or through PV conductors or raceways containing live PV conductors are also a safety concern. The NEC permits single conductor PV wire to be exposed in non-accessible outdoor locations, such as rooftops and ground-mounted arrays. When the PV circuits are run inside the building, the conductor must be contained in a metal raceway. When PV wires are run beneath a roof, they shall not be installed within 10 inches of the roof decking or sheeting, except where directly below the roof surface, covered by a PV module and associated equipment. The 10-inch requirement is to prevent accidental damage from saws used by firefighters during roof ventilation. It is important to also note that it is a requirement in the new 2011 version of the NEC, and older installations may not have complied with this new requirement. Inhalation exposure, due to the manufacturing process, includes the use of hazardous. Also look for access for ventilation while on the roof. You still want to ventilate at the highest point over the fire, but without cutting through the PV array if possible. Flat roofs with complete PV coverage, you want to look at horizontal ventilation with fog spray and/or positive pressure fan ventilation. Fire and extreme heat will also affect the structure of the module. The high temperatures may cause the metal to warp and the modules to come loose from their anchor points, causing them to dangle or fall. Fire could also damage the wiring insulation and melt the aluminum mounting rails, resulting in a possible loss of ground continuity, energizing the module frames and mounting rail. Leave the scene in a safe condition. If a system was damaged during a fire at night, when exposed to sunlight, it will begin to generate electricity. This is where tarping comes into effect. Looking at this roof, we now have to add the metal roofing into a hazard if it comes in contact with an exposed wire. If you're going to cut a hole in this roof, make sure that you're not tripping and don't inadvertently pierce any of the panels. As you see on this picture, there is no ventilation spot on this roof due to this installation. When dealing with a fire either under or involving a PV system, always utilize SCBA, and remember you can use a minimum of a 10-degree fog pattern at a distance of 5 feet. On this picture here, there's not much room for vertical ventilation. This is where other options need to be considered. You can look at skylights, scuttles, smoke vents, or use a positive pressure fan and/or a fog nozzle to ventilate. Where would you perform your roof ventilations on this installation? Hopefully, the other side is clear of any solar shingles. We need to also consider motor vehicle collisions when looking at solar fire safety. As you can see, this car drove into a ground-mounted system and has now damaged the modules. It now has the possibility that the car has been energized with electricity, no different than a downed power line. As you can see in these pictures, this is a clear indication of why you do not want to try and cut conduit or wiring at any time. Disconnect is always your best option. All these tools that we commonly carry and would utilize to cut any kind of conduit or wiring all resulted in sparking, arcing, and causing a fire on the adjoining 2x4, as well as conducting electricity back to the user. If you were to pierce a panel as you see here with a pickhead axe, you can actually see there is current coming back through the fiberglass handle going to the operator. Panels that may appear damaged, as this one as a result of a fire, still produce energy, as you can see, due to the voltage of DC coming from it. So in summary, pre-planning is essential. This will let you know which facilities have solar systems and how they operate. If a system is present, you want to notify the incident commander and responding units. When a sufficient light source is present, panels are energized. Scene floodlights can create dangerous levels of electricity if not monitored. You don't want to intentionally break the panels or cut the conduit at any time. And contact with damaged systems are dangerous, even if the fire is out. Stay away. For removing a panel, you want to shut down the AC power, turn off the inverter. Some hold capacity for 15 minutes, so you may have a wait time. Do not break at any time, but remove the panel. Do not cut the wires, but disconnect them. And also cover the panel to shut it down in case of any residual light sources. Thank you for watching this presentation. If you have any questions, you may contact us at delmarvaetc@gmail.com. You also may reach out to us on Facebook or Instagram by going to our page, Delmarva Emergency Training Concepts, or delmarvaetc.com. Thank you. Have a good day.